Waiting. Okay, and we are live.
Great. So
I'll also start the. You started the recording. Okay.
Started the recording. So that indeed is just about all I wanted to say today. Welcome everyone to the fourth OOPS session of the week. So today we will have two lectures. Both are being recorded. So if you don't wish your audio and video to appear in the recording, please keep your microphone muted and your video switched off. And let me just also mention that next week we have a rather full week of OOPS material with a mini course from Ivan Corman, Monday, Tuesday, Wednesday, followed by several short lectures on related topics on Thursday and Friday. So there will be an email to the mailing list about that this afternoon. With that, I'm going to hand it over to Nina Gantert to introduce the speakers. Over to you, Nina.
Yes, thanks, Luigi. So today we will have two talks, and the first speaker is Piotr Dyszewski. The second is Sam Johnston. You can see them both here. And Piotr, who is a postdoc in Munich right now and also in Wrocław, will start, and his topic is branching random walk and stretched exponential tails. And the screen sharing works for me, and I hope for you as well. Okay, Piotr, you can start.
All right, thank you, Nina. Yeah, so for the most of the Nina's lecture, she focused on a branching random walk where the displacements have thin tails. And what I want to do today is to show you how you can work with branching random walks whenever your displacements have heavy tails. And what I mean by that is whenever the exponential moments exist or not. All right. So first off, let's just recall the setting. So we will work on a real line, and we start with one particle at the origin, and after some time, this particle dies and gives birth to a random number of new particles. And we're going to assume that the reproduction law is the reproduction of the particles. It's governed by a supercritical Galton-Watson process. So this in particular means that the mean of the reproduction law is greater than 1. All right, and we're also going to assume that the displacements of the particles, because after the particles are born, they are moved somewhere on the real line. All the shifts are an IID copy of one given random variable with so-called stretch exponential law. So this means that the tail of x decays as e to the minus t to the power r, and this twiddle means that the quotient of the both sides tends to 1 as t tends to infinity. So instead of giving you a full scope of what happens with heavy tails displacements, I'm just going to focus on the stretch exponential case and give you the whole treatment. But most of the phenomena do replicate with different tails. All right, so the dead particles are removed from the system, right? And then they reproduce as previously. So they produce some random number of other particles, which are then placed on the real line. And this system evolves for some time according to this rule. And after some time, you do get a collection of particles on the real line. And the aim is to somehow understand how this collection of particles evolves, right? And the first question you want to ask is the behavior of the extremes. So in our case, this is going to be the position of the rightmost particle. And this, this case study of stretch exponential displacements basically boils down to explaining the math behind the result that I did obtain with Nina Gantert and Thomas Höfelsauer. All right, so Nina Nina needs no introduction, and Thomas is her former PhD student, and if my memory serves me right, he did graduate 2 years ago, and now he works in the private sector. All right, so under some technical assumptions that I do want to omit because I don't want to make my slides too complicated. We have the following. So assuming that the law of this generic random variable is stretch exponential, and that this guy is centered and has variance 1, and then it turns out that you have 2 different regimes of the behavior of your rightmost particle. So depending on whenever r is smaller or greater than the critical value of 2/3, your rightmost position either fluctuate or you have almost true behavior. So in both cases, the leading term is the same. This is alpha times n to the power 1 over r, right? But for smaller values of r, the rightmost particle fluctuates in the neighborhood of this value, with a limit being the shift of a Gumbel law. So here, this w, this random shift, is a martingale limit associated to the underlying Galton-Watson process, and we will see exactly how this guy pops up. And whenever r is big, you have more balanced behavior, which translates to a almost true limit. All right, so let me just introduce the setting that Nina did give in order to be self-contained. So let Zn be the underlying Galton-Watson process. All right, so maybe I want to go back and say 2 things. So first of all, my aim here is to somehow explain where this exponent are coming from, and where this different type of behavior is coming from. But most importantly, I do want to give you some idea of how can you use the heaviness of your tails to your advantage when you study the branching random walks. All right, so as I said, let Zn be the underlying Galton-Watson process, and assume, just for the simplicity, that this process never dies out. So assume that the probability that your descendant has no children is 0. And if we don't have this assumption, then everything that I'm going to tell you will still work. However, you will just have to condition on the set of survival of your population. All right, so then you can draw your Galton-Watson tree, right? So then, and you assign labels to each of the individuals. So of the individuals. So let's say that the first particle has a label which is an empty word, and then particles from generation 1 has a label which is a string of length 1. Then particles from generation 2 has a label which is a string of length 2, and so on and so forth. So once you have those, once you have your Galton-Watson tree, then you take the displacements. So you take those a family of IID random variables and assign them to the edges of your Galton-Watson tree. So you think of of your labels of your x's as the displacement of a given particle from the place of birth. All right, and then if we are interested in a position of a particle from generation n, then what you need to do is you just look at the label on your tree, look at the path from this particle up to the root, right? And you just sum all the displacements along this path, right? And then you get this quantity, which I'll denote by Vx, which represents the position of the particle with label x. And now your rightmost particle is just the maximum of those guys. All right. So one technical thing that we're gonna need is the large deviations for random walks. So you've seen that in Nina's course, and she did use large deviations in the case when the displacements have thin tails, when you have some exponential moments. And this is basically a common knowledge, right? In the case which I'm looking at here, that is the stretch exponential case. This is not so well known, so let's just look at what's happening. So the lack of this exponential moments, morally, this translates to the so-called principle of one big jump. Namely, if you look at a statistic, a reasonable statistic of your ensemble, then the probability that this statistic is big in some sense is asymptotically equivalent to saying that one of the guys in your ensemble is big. So, for example, if you look at the probability that the sum of the two guys is big, this is asymptotically equivalent to saying that one of those guys is big. And now we want to somehow try to push this phenomena and see if we can get some large deviations result out of that. All right, so let's take Sn to be the sum of those xk's, right? And take the maximum and denote it by xn star. And now we want to understand, what's the probability that this Sn is greater than some threshold Tn. And as it will turn out in the future, we don't need the full scope of Tn. It will be sufficient for our needs to take T of the form C times n to the power 1 over r, right? So we want to somehow exploit this principle of one big jump. And naively, what you can do is say, okay, so the biggest displacement does something, right? And then the other displacement somehow contribute, right? So you can naively try to write this supremum and just see what happens. Yeah, so we know what is the behavior of this maximum, right? This is exactly this part. And then you check what's the behavior of the rest of those guys. And since you think of those guys as the typical displacement, right? You expect a Gaussian behavior from that. All right, so you have some expression in your exponent, and you just simply optimize this guy, right? And what you get is exactly that. All right. All right. Yeah. So now, when you look at this probability of typical particles, what you can do is since you expect this Sn to be close to Gaussian, you can write Sn minus 1 divided by square root of n, and this is supposed to be greater than this constant that we somehow get times n to the power 3 over 2 minus 1 over r. So you can actually see from that the value of r is being equal to 2/3. It's somehow critical for the behavior of the deviations, and this is exactly this critical parameter that we have in our result. All right, so you write down what's the behavior of the the product, right? And this leading term from the maximum translate to the leading term in the exponent, and then those smaller guys somehow transfer to something something smaller. So the key fact here is that the leading term is the asymptotic of the deviations of Sn really comes from the maximum, and then depending on the value of your parameter, then you can get something different or not. All right. So what can we do with that? Well, we can redo the first term of the asymptotic of the rightmost particle, and this is again something that Nina did in the previous course. But still, this will help me drive my point. So let's just do that. So the probability that Mn is greater than c times n to 1 over r, and 1 over r is the correct scaling because I said so. So you look at the probability that one of the guys is greater than this threshold, and you can use the first moment method to bound this basically by a expectation of the number of guys that are greater than this threshold, right? And what you get is the expectation of Zn, which is roughly m to the n times your deviation. And this is something that we did compute just now, right? So what we get is asymptotically n to the n times e to minus c to the power r times n, right? So now we need to tailor this Cn such that this term compensates this m to the n, right? And this leads to basically a prediction of the first order term being n to the power 1 over r times alpha, and this alpha is exactly given here. All right. So what we can learn from that? Well, everything this first term really comes from this parameter, right? And we just said that this leading term, this asymptotic of the deviation, comes from the biggest displacement. So we can try to argue that the first term, the asymptotic expansion of the rightmost particle, is related to the biggest displacement in your collection. And this biggest displacement, right? This is just a maximum of IID guys. And the only twist is that the number of guys that you are considering is random. But since those two quantities are independent, this is still easy to handle. So you know that after a proper centering and scaling, you will see a nice limit, which is again a random shift of the Gumbel distribution. And this is something that's so easy that we can actually try to prove that. So, for instance, take some threshold xn that goes to infinity, and let's just try to compute the probability that this biggest displacement is below this threshold. Right. So what you do, well, you just condition on your tree. Right. So this leads you to writing that basically you are saying that you have a random number of guys that are supposed to be smaller than this threshold xn, and this random number of guys is just the number of the edges that you have up to time n, right? And this is easily expressed in terms of your branching process, right? And then looking at the expression under the expectation, it behaves as e to the minus the product of this yn and the tail of x. All right. So now the random shift comes into play, because we know that this yen behaves pretty nicely. That is, after scaling by m to the n, you get a martingale, and since this guy is non-negative, it will have a almost row limit. Moreover, since I'm implicitly assuming that the Kersten-Stigm condition, this limit will be non-negative. So this Kersten-Stigm condition is one of those ugly assumptions that I just omitted in the second slide. All right, but now we know what the behavior of this yn, right? This is again something that grows in the same fashion with a random shift. All right, so now we can take a very concrete threshold here and just start to compute things. So first off, we do only the simple bits. I mean, first off, we just take the asymptotic equivalent of yn. This is here, and we just plug in the definition of xn. So nothing happens. Then we look at the exponent on the right-hand side, and we simply use the Taylor expansion. And when we do that, we notice that this exponent here is tailored such that it will cancel with a derivative that pops up from the expansion, right? So you're left with a constant. All right, but now we just need to recall what is the role of alpha. Alpha is taken such that this guy will cancel with m to the n, right? So we are in business. We're in business because if we call our constants accordingly, then we get a nice limit. And if we go back to what we have done, this basically shows that this biggest displacement after a proper centering and scaling does converge to this nice random shift of the Gumbel law. So as you can see, the analysis of the biggest displacement is pretty straightforward. So what can we do with that? Well, when we look at the first order asymptotics of the biggest displacement and the rightmost particle, they are the same. So it's not difficult to convince yourself that if you look at the positions of the particles which didn't have a big jump along the branch, those guys are negligible somehow, right? And if you have that, then you know that you need only to concentrate on the particles that had a big jump, right? And how many are there? So all the particles up to time n, which we see in our system, the number of those is roughly m to the n, right? And then you look at those particles that did encounter a big jump, and those will be fewer, right? And it turns out that whenever r is small, you only see a polynomial number of these big jumps. And whenever r is big, you see something which is almost exponential, but not exactly exponential. And I do know that this line is somehow vague, because I don't tell you what do I mean by x having a big jump. So the takeaway message from this line is that for small values of r, we have small number of big jumps that contribute, and for big values of r, we have a lot of big jumps that can contribute. All right, and in the end, those particles that did give a big jump form a small subset of the whole tree. So what can we do with that? If we look at the whole tree, the first step that you want to do is look at those particles that with the displacement comparable to the first order asymptotic, and color the edges green. Then you color the edges which are below in red, and then you look at the path that goes from the green edge to the root, and you have an orange segment and a blue segment. And the way this orange color and the blue color works is that when you take into account other big jumps, what you will see is that you have a segment which is orange and which is disjoint from different paths, right? And the moment they start to meet each other, they will be painted blue. So the thing is that those orange guys are independent. Yes?
Piotr?
Yes?
Gut?
Were you trying to ask a
Should
question,
be.
Nina?
Oops. Let me, there's a question in the chat. No?
Yes? What's the question?
I don't see a question. I think you can
Maybe it was
continue,
sent
Piotr.
privately, but
I
Okay.
don't see a question in the chat.
Okay. I'm all right. So I'll just move on. Where was I? Yeah. So the orange guys are basically independent, and those blue guys are the bits when you see some kind of dependence. And yeah, so the set of those admissible particles, I mean those that you see at the very end, right? Each of those positions of those guys actually can be decomposed in the following fashion. So you have this when you go along here, you see a blue path, as path in the orange color, then is this one green big jump, and then there's the red path. All right. So what's the contribution of each color? So if you really believe that those big jumps are a subset of your random tree, this means that if you take two green edges, they will be far away from each other on the tree, and this means that those paths will meet very high up. Hence, this blue bit will be relatively short. In conclusion, this red part is negligible. So now let's focus on the red part. And this is something that requires some computation, but since the maximal displacement grows faster than linear, right? This grows like n to the power 1 over r. When you look where those displacements happened, I mean, in which generation, it's more likely that they will happen in a generation which is close to n. So this in turn tells you that those red segments, they also be relatively short. So this red guy can also be neglected. All right, but this tells us that the positions of these admissible particles asymptotically are just the orange parts and those green jumps, right? And those guys are independent. So we are quite happy. So now we need to compare those two, right? So you know that asymptotically your rightmost particle is consisting of these big jumps, this nx, and the position of the typical particles. And you know that this big jump, well, it is big, and those typical particles, this is their behavior should be asymptotically normal. So you can do the same optimization game that we did previously, and you would come to a conclusion that the contribution of those typical particles, it is also of the order n to the 2 minus 1 over r. So this is the exact same exponent that we did get from this optimization. On the other hand, we know what is the behavior of the biggest particle, right? So this is, we have the leading term, and we know what are the fluctuations. So now we just need to compare those two, right? So if r is small, then whatever the contribution of the typical particles is, it's killed by the fluctuations of the biggest particle. And this rightmost particle, it scales the same as the biggest particle, and you get this nice limit. Moreover, there's one comment that I would like to make at this point. That is, we can actually show that the difference between the rightmost particle and the biggest displacement is negligible in compared with the order of the fluctuations, right? So this Mn, this is something that consists of, the maximum of your guys, and this Mn, this is something that has, the sums. So this line somehow really screams that one particle did all the job. All right. So what happens when R is big? Well, you need to go back to our picture, right? And what you do, you first look at the green displacement, at the green edges, right? And this fixes the first order, right? And then you know that the contribution of the orange parts should somehow kill the fluctuations of those green guys. So what you can do is start looking at those orange paths and see whatever is the biggest. And as I mentioned, in this case, there are actually a lot of those green jumps. Hence, there will be a lot of those orange paths. So you have a very big number of those orange paths, which in turn gives you a more balanced behavior. And now you can basically play again the same optimization game and say that, all right, so this the contribution of those orange guys is in fact of the other 2 n to the 2 minus 1 over r, right? And if you do this optimization right, you can squeeze out the limiting constant. All right. So what happens in the boundary case? Well, you notice that both of those exponents are equal 1/2, right? So now, if the contribution of the typical particles is of this order, then you would conclude that they will actually fluctuate. All right. So but still you can work around that, right? You can take a family of independent Gaussians, and if you look at the rightmost particle after centering and scaling, you will see again a maximum of the those admissible particles, right? So you see the proper centering of the rightmost position, and then those typical displacement would be asymptotically Gaussian. But remember that we did decouple the whole thing, right? So we can still basically work as if we would be working with a family of independent guys, right? So still, centering this rightmost particle is the same as the cumulative distribution function of the rightmost particle is the same as those big displacements with some random Gaussian shifts. But still, this is something which is manageable. So you do the exact same computations that we did for the maxima, right? The only thing is that this Gaussian shift transfers to this integral, and here this big displacement transfers to this e to the minus e, pardon, and then the Gaussian random variable transfers to this Gaussian term, right? But still, if you look at this integral as a function of t, this is still a constant times e to the minus t. So nothing really changes. I mean, those fluctuations, they do contribute, but the contribution can be hidden in a constant. All right, so this is that. I mean, in the case where r is very small, right? The behavior of the whole system is really governed by one big jump, right? And in this boundary case, this one big jump is supplemented by this Gaussian shift. However, this contribution can be hidden in this constant gamma. So in particular, this gamma it is not a continuous function of our parameters. Right, and if r is big, then you have a lot of the typical particles that somehow contribute, which gives you a more balanced behavior. Yeah. So remember that the way that we started our analysis is first by looking at the biggest displacement. And on one hand, it did give us, all the information we needed, or it allowed us to decouple the whole thing. And this was the key step which we needed in our analysis. All right, so this was based on a joint paper with Ina and Thomas, and it's available on archive. And let me just mention that this first order asymptotic was established by Nina in the 2000s, and the large deviations for the stretched exponential random variables go back to the Nagaev in the late 60s. However, it's not an easy thing to read. All right, so I'm out of slides, so I guess this is a good place to stop. Thank you.
Thank you very much, Piotr. So maybe you can unmute people, Omer. And so are there questions to Piotr as long as the screen is still shared? Some questions were already answered in the chat, I see. Seems that there are no questions.
Piotr, you are muted currently. But...
Yes, I noticed. Yeah.
So we will stop.
It seems that there are no questions right now. So then I think, you stopped the recording for questions.
I will stop now the recording and start it again for some talk. But...
Okay, but